Hello and welcome to this lecture in my series on the satisfiability problem for fragments of first-order logic. My name is Pratt-Hartmann and today I'll be talking about the guarded fragment. I'll be explaining why the satisfiability problem for this fragment is decidable, and I shall give an upper complexity bound. I won't be going through the proofs line by line. If you want to do that, then here you see a reference to a textbook where you can find all the details. I'll concentrate on the main ideas. As usual in these lectures, I shall assume basic understanding of first-order logic and complexity theory. The guarded fragment, usually denoted GF or sometimes just G, is a fragment of first-order logic in which all universal quantification has the form shown here, and all existential quantification the form shown here. So let's have a look at the universal quantification first. We see that we have a tuple of variables which are universally quantified, and we have some formula to which that universal quantification is applied. We shall insist in the guarded fragment that that formula has the form of an implication where the antecedent is an atom, that is an atomic formula, containing all the variables of the consequent. Similarly for existential quantification, but here we assume that the formula to which the existential quantification is applied has the form of a conjunction, where the first conjunct is an atom containing all the free variables of the second conjunct. So let's have a look at some examples here. So these two formulas that I'm pointing to now are in the guarded fragment. Let's have a look at the first one. We've got an existential quantification applied to just a single variable, and we will notice that this has the form of a conjunction, and the first conjunct is an atom containing that variable. The second conjunct is universally quantified, and so we've got universal quantification here, but notice that the formula to which that is applied has the form of an implication, and we see that the antecedent of that implication has as its free variables x and y, and that contains all the free variables of the consequent, in this case just y. So that says every artist admires some beekeeper. The second formula again is guarded. The main quantification is universal, and we see that the formula to which that universal quantification is applied is an implication. The antecedent of the implication contains all the free variables of the consequent. The only free variable in the consequent is x, and so that x is contained in that antecedent here. And if we look at the consequent, that itself is universally quantified, and again we see that the universal quantification has the form of an implication. The consequent of that implication has two free variables, x and y, but those two free variables appear as arguments of this atomic formula here, which forms the antecedent, so that formula likewise is guarded. And finally, here we have two examples of formulas which are not in the guarded fragment. And we see that this is not guarded because if you look at this universal implication here, we see that the consequent has two free variables, x and y, but although the formula to which the universal quantification is applied is an implication, the antecedent of that implication does not have x as one of its free variables, so that's not guarded. And similarly, let's have a look at this one. So this says some artist envies every beekeeper who does not admire him, whom he does not admire, I should say. We'll see that that is not guarded because the consequent, this implication here, doesn't have the form of an atom, right? So we have this is an atom, but the whole antecedent of the conjunction is a conjunction. So that formula is not guarded. It is not of the form indicated here. Okay, so that's informally what the guarded fragment is. Let's have a look a little more precisely. So we define GF to be the set of all first-order formulas closed under the following rules. First of all, the guarded fragment contains all atomic formulas. Secondly, it's closed under Boolean combinations. Thirdly, if psi is a formula of the guarded fragment and G is an atomic formula such that the free variables of G include all the free variables of psi, and X bar is a non-empty tuple of variables such that the free variables of G include X bar, then we'll allow for all X bar G implies psi to be, that formula will be in the guarded fragment. And similarly, there exists X, G and psi. Well, that will also be in the guarded fragment. And finally, we have one last rule here, the fourth rule. And this says, if psi is a formula of the guarded fragment with one free variable, then we can quantify that variable without any kind of special atom G here. As normally we restrict quantification, but if there's just one free variable, we can quantify freely. We do allow equality in this fragment, and we allow also individual constants. Normally, I shall be dealing with the case where there are no individual constants because they don't really add anything interesting. We do not allow function symbols. The atoms G in this construction, so the atoms G as they appear in these formulas here, for all X bar G implies psi, and there exists X bar G and psi, are called guards, hence the name guarded fragment. So in the guarded fragment, all quantification, universal or existential, is relativized by atomic guards. We do allow equality as a guard. So we can have guards of the form x equals y, or even x equals x if we like. Notice the final clause in the definition of the guarded fragment. If psi is a sentence in the guarded fragment with just exactly one free variable, x, then we can quantify that variable without a guard at all. And that's justified because if x is the only variable occurring in psi, we can employ equality guards to do more or less the same thing. So instead of saying there exists x psi, we can just say there exists x such that x equals x and psi. So that since x equals x is allowed as a guard, that's a guarded formula. So we may as well allow, we don't really require a guard with existential quantification of formulas containing just one variable. And similarly with universal quantification, for all x psi, if x is the only variable occurring in psi, then I can take for all x psi to be equivalent to for all x, if x equals x, then psi. So that effectively is, that's also guarded. And so we don't need to worry about this extra clause allowing universal and existential quantification freely when there's only one free variable. We might as well have it anyway. If we restrict ourselves in addition to have just k variables, then we have the k variable guarded fragment, which I'll denote GF with superscript k. So it is simply the intersection of the guarded fragment and the k variable fragment of first order logic. So it's like the guarded fragment, but we only allow variables x1, x2 and so on up to xk. So we have a sub-fragment here. Now a formula in the guarded fragment will be said to be in guarded normal form if it has the following shape. This is rather a complicated formula, so let's go through it step by step. So the first formula, first conjunct here, we have three groups of conjuncts really. The first conjunct is simply a formula which says there exists x bar such that chi of x bar. Chi is just any old formula, but remember this whole formula is in the guarded fragment, so this formula chi will have to have a guard in it. It will have to have the form of a conjunction, at least in the case where there's more than one variable in this tuple x bar. So I'll call this conjunct the initial conditions. It just says that some things exist. Remember, this is a guarded formula, so that formula chi will have to have a guard in it. Okay, let's look at the next group of conjuncts. So we see here that we have formulas, these blue highlighted formulas. We have a collection of them indexed by h, where h runs from 1 to l. And the hth such conjunct has the form of universal quantification. Of course, it has to be guarded, so there's some atom, right, with a tuple of variables applied to it, and that tuple of variables has to have contain all of the variables that occur free in the resulting consequent. What is the consequent? Well, the consequent is existentially quantified. Again, we've got the tuple of variables, call that yh, and these variables will be applied to this existential quantification will be applied to some formula chi h, and chi h I'll take to be quantifier free. So this is a universal existential formula. There's an antecedent, so it's guarded. The universal quantification is guarded. This whole formula has to be guarded, so there has to be, at least if there's more than one variable here in this tuple, there'll have to be a guard in this formula chi. That's fine. You can assume there's a guard there. And the free variables of the formula chi are just the formulas in h, together with some extra ones which we've quantified, so xh, together with some extra ones which we've quantified, namely yh. And there are no other free variables in chi, because they will have to be mentioned in this tuple here. Okay, so we've got an atomic formula, we've got a existentially quantified formula, and the whole thing's universally quantified. So this is a nice guarded formula, and we have L of these. And I'll call these things the witness requirements. So we've got initial conditions and witness requirements. Witness requirements because it says that any tuple satisfying some atom has to have a witness, let's say yh, satisfying some quantifier-free formula, together with the tuple satisfying the atom, of course. Okay, so that's the second group of conjuncts. The final group of conjuncts, these ones illustrated here, again they'll be indexed by h. H runs from 1 to m. They're now universally quantified, so we have a tuple of variables, let's say zh. Again, ch of zh will be an atom, so it will just be an atomic formula, and omega h will be some quantifier-free formula involving no variables other than the zh. So again, this will be guarded, and the whole thing will therefore be guarded. There'll be no problem there. Okay, so though that is a so-called normal form guarded formula. It's a guarded formula having this shape. Now, we can prove a lemma if we have a sentence, let phi be a sentence of the k-variable guarded fragment. We can construct, in time bounded by a polynomial function of the number of symbols in phi, a normal form formula, psi, of the k+1 variable guarded fragment such that phi is finitely satisfiable if and only if psi is. The proof proceeds in exactly the same way as for the two variable fragments where we considered so-called Scott normal form. So if you're interested in the details of the proof, then I refer you to the lecture on the two variable fragment, but it's essentially the same strategy. Namely, what we do is we take a formula phi in this case in the k variable guarded fragment, and we successively replace the innermost quantified subformulas with new atomic formulas involving fresh predicate letters. So, thus, to determine satisfiability of formulas in the guarded fragment, it suffices to restrict attention to formulas in guarded normal form, as shown here. And I'll now proceed to show that the satisfiability problem for the guarded fragment is decidable. More specifically, I'll develop a procedure which I'll call SAT-GFK, which takes as input a guarded normal form formula phi and returns yes if that formula is satisfiable and no otherwise. And the procedure will employ the apparatus of k-types, or atomic k-types. I'll just say k-types in this lecture. I talked about these in an earlier lecture, but by way of revision, a k-type over a relational signature sigma is a maximal consistent set of equality-free literals over that signature involving no variables other than x1 up to xk. So in my definition of k-types, I do not allow equality. Recall that if A, fractor A, is a structure interpreting the signature sigma, and A bar is a tuple of elements, then there is a unique k-type satisfied by A bar in that structure, and I'll denote it by this symbol here, type fractor A, and then the tuple in question. Okay, so that's the unique type, the unique k-type satisfied by A in the structure fractor A. I'll call a k-type guarded if there is a predicate P in our signature such that the atom P applied to W is in the k-type Tor for some tuple W containing all the variables x1 up to xk in some order, and I do allow repeats. So all I require is that for a type to be guarded, all I require is that there is some positive literal in that type whose arguments cover all of the variables x1 up to xk. Repeats allowed, any order. It just has to cover all of the variables. That's a guarded type. In a previous lecture, we were encouraged to think of types as complete specifications of the relations determined by some structure on a particular collection of elements, usually distinct individuals. But sometimes it's easier to think about types as structures. I mean, types are sets of atoms involving variables, but we can think of the variables now as objects. And those objects, x1 up to xk, form the domain of some structure. So you can now think of a type as a structure in the obvious sense. For any predicate R in the relevant signature with arity M, and any M tuple over these objects, these which are now variables, will take that tuple to satisfy the predicate R in this structure, just in case the relevant literal R applied to W is in the type. So technically a type is a set of literals, but we can think of a type as a little model, as a little structure whose domain is the set of variables themselves. If Tor is a guarded k-type, then in the corresponding structure there's some predicate of arity at least k satisfied by a tuple featuring every element of the structure at least once. Okay, so here's the next idea which we need to develop our algorithm. If x and y are sets, we'll write rho colon x strange looking arrow y to indicate that rho is an injective partial function from x to y. So rho maps its domain, dom rho, bijectively to its image, im rho. So dom rho will be a subset, in general a proper subset of x, and rho will map that subset to some set of objects in y, and the mapping will be one-to-one. So you can't have two objects mapped to the same value. Okay, so we get a bijection between the domain of rho and the image of rho. Now let sigma and Tor be types over some signature sigma, as we had before. Suppose sigma is an L type and Tor is an M type. If rho is a partial function from the objects x1 to xl to the objects x1 to xm, then we'll call rho a partial isomorphism, and we'll write rho colon sigma strange looking arrow tor if for any tuple w bar chosen from among the elements of the domain of rho and any predicate p of samiarity as the tuple w bar, a w bar satisfies p in sigma just in case the image of w bar under rho satisfies p in tor. So we can think of, in this case, where if there's a partial isomorphism, if rho is a partial isomorphism from the type sigma, the L-type sigma, to the M-type tor, what that means is that there's some substructure of sigma. If we think now of partial types as if we think of types as small structures, there's some substructure of sigma which has a copy in tor. That's basically all it says. And the idea behind our algorithm is that if you've got types which are related by partial isomorphisms in this way, we can patch those together. Okay, so let's now fix some formula phi in guarded normal form as before. Initial conditions, existential requirements, universal constraints. And because this is rather long to write, I'll abbreviate things, and I won't be talking about universal constraints very much, and I won't really need to get into the details of them very much. So for the moment, I'll just abbreviate all these universal constraints with a single letter, upsilon. So upsilon just means these universal constraints here. So whenever you see upsilon, you can mentally project this big conjunct here if you can remember it, because that's what it will mean from now on. So this is the formula in normal form which we're given. Just the universal constraints have been compressed, just represented by a single letter. Okay, so next idea. So if we remember that these universal constraints are upsilon of our original formula phi, let's define the set T to be the set of those guarded types of arity at most k, the number of variables occurring at all in phi, satisfying these universal constraints. So for all tor in set in T is a set of types of arity up to k. For every type in that set, we'll have tor makes upsilon true. Now you might think, what do you mean? Tor makes upsilon true. What does that mean? Well, tor, remember, is a structure. We can think of a type as a structure. It's a small structure on the elements x1 up to xk, or x1 up to xl if it's an L type. So that structure either makes the universal constraints true or it doesn't make them true. This is a sentence. So either the sentence is true in that structure or it isn't. If it's true, then we put the type in question in T. If upsilon is false, we don't. So T is just those types satisfying the universal constraints, upsilon. Clearly the number of them is finite. For the moment, let's just write it as Z. Doesn't matter what it is. We'll worry about the just how big this is later, but it's clearly finite. So what we'll do is we'll start T off. T is going to be a variable in our algorithm, and we'll start T off to be the set of all of the types of arity up to the number of number of variables in phi, and we only look at those types which satisfy the universal constraints. And there's a finite number of them. And gradually, as we go through the algorithm, we'll throw away elements of T. So let's see how this works. So let's go back to our original formula phi in normal form. And remember, it has initial conditions, existential requirements, and the universal constraints. Let's look at any one of the existential the witness requirements, the existential requirements here, so they all have this form. Yeah, so this is the one indexed by h, where h is some number between 1 and L, I think was the limit. Okay, so now suppose that sigma is a type in T. T is the set of types which obey the universal constraints, remember. So if we take any tuple of elements W prime, right, so let's suppose that, I'm sorry, I'll start that again, right? Let's suppose sigma is a type in T and W a tuple of elements chosen from the variables of sigma, satisfying the atomic formula AH, where AH is the guard of the hth witness requirement. We'll say that an H witness for W bar in sigma is a type Tor such that there exists a partial isomorphism rho from sigma to Tor, with the domain of that partial isomorphism containing all the variables occurring in W bar, and a tuple V bar of additional variables of Tor such that the image of W bar together with V bar satisfies chi H, this formula here, occurring in the witness requirement, in the type Tor. Okay, so if you've got a type sigma in the set T and a tuple W bar satisfying some atom of interest, the guard of one of the witness requirements in this type, which remember we think of the type as a little model, then there has to be another type, Tor, such that if you take the image and the partial isomorphism rho from sigma to Tor, so such that if you take the image of W, we can find additional that's rho W bar. We can find additional elements of Tor V bar, such that rho applied to W bar together with V bar satisfies chi. In other words, Tor contains witnesses which will make this true. Now, of course, we haven't got a model here. We've just got types which are a little mini models, and they're completely separate things. So that we're not dealing with a single model that we've got to make a model, and this is a purely formal relationship between types. So an H witness. So that I've simply defined the notion of an H witness for a tuple W bar in a type sigma. And that's a type Tor satisfying the conditions that I've just outlined. Okay. Why do we want to do this? I mean, what's going on here? The idea is that models related by partial isomorphisms can be merged. So if we've got a type here, which again we think of as a small model, a type Tor, which we think of as a small model, and a partial isomorphism between them, we're going to merge the two together so that they become a single model, and the idea is that we identify the elements in W bar, the elements W bar of sigma with their images under this partial isomorphism, and we'll be able to perform this identification simply because it is a partial isomorphism. That is, elements satisfying any predicate here will be such that the corresponding elements in this structure, in this type Tor, satisfy exactly the same elements. So we'll be able to just identify them. That's the idea behind partial isomorphisms. Okay, now we're starting to get towards the algorithm. Say that a type sigma in our set of types T is good if, whenever we have some tuple satisfying the guard of a witness requirement, so AH is the atomic formula which is the guard of the hth witness requirement. when we if we have a tuple satisfying one of these guards, then there exists an H witness for that tuple in the set T. So there is an H witness for sigma. For the tuple W in sigma somewhere in the set T. Otherwise, we'll say that sigma is bad. So a type is good if whenever it has a tuple satisfying a guard for the Hth witness requirement, there is a witness for that tuple. So to decide whether phi is unsatisfiable, we proceed as follows. Start off with T being the set of guarded types of arity at most k satisfying the universal constraints. Remember, the universal constraints, which I'm abbreviating by epsilon, come from our original formula. It doesn't really matter what they are. There's only finitely many types of the relevant arity at most k. So we just list them. You can check whether they satisfy the universal requirements or not, and so you can compute the set T. Now, if T contains any bad type, that is a type for which there's a tuple satisfying a guard for a witness requirement and no witness for that tuple, then if it's bad, that is, if it's bad, we will chuck it out. So if T contains any bad type, so pick some bad type and throw it away. Now keep going, continually checking to see if there are any bad types. Notice that when we do this, types which were previously good may become bad because we may have removed things which were witnesses for them. I mean, sigma might have contained a tuple W, which has a nice witness Tor, but we may then have removed Tor because Tor itself was bad, and then sigma may become bad. So as we keep removing bad types from the set Tor, previously good types may become bad. We'll just keep going until we can't remove any bad types. At the end of that process, and since T is finite, there must be an end to that process, we'll have a collection. T will be a smaller collection of types, and we just check to see that at least one type, sigma in Tor, satisfies the initial conditions. In other words, sigma makes the sentence, there exists x bar chi of x bar true. These initial conditions, remember, are come from the formula phi, which we're checking. So here's the procedure in more detail. So it's called GFK inputs phi. The phi is a normal form guarded formula with at most k variables, and we remember that this normal form formula has the initial conditions, the witness requirements, and the universal constraints. And we set T to be the set of types of appropriate arity satisfying the universal constraints. And until it contains no bad types, find the bad types, chuck them out. So T is now T minus all the bad types, and you just keep going. At the end, T cannot contain any bad types. So then you do the following test. If T contains a type which satisfies the witness requirements, return yes, phi is satisfiable, otherwise return no. Then finish. Since T is initially finite and gets smaller with every iteration, clearly this algorithm terminates. And our first task is to show that it terminates with yes, if and only if phi is satisfiable. So let's have a look at this. So we have a lemma, let phi be a normal form sentence of GFK. If phi is satisfiable, then the algorithm sat GFK returns yes. To prove it, we'll let A be a model of phi. Remember, we're assuming phi to be satisfiable. Let T0 be the set of types of arity at most k realized in A. So we claim that the invariant T includes T0 holds throughout the loop. Remember, T is the T is the variable in the in our algorithm containing a set of types. So I claim this invariant holds. So we'll suppose otherwise and derive a contradiction. Since A makes all the universal constraints true, I mean, after all, it's a model of phi, then we know that every type realised in T0 satisfies the universal constraints. So certainly initially T0 is included in T, because T is the set of all types containing the universal constraints. So initially this invariant holds. So if it fails, then there'll be some point at which a bad type in T0 is ejected from T. The only things that ever get ejected are bad. And since sigma is bad, there'll be some tuple of variables w bar and some h, an index of one of the witness constraints, such that the tuple of variables w satisfies the guard on the hth witness constraints in sigma, and sigma will be bad. There won't be a witness for this tuple, and since sigma is in T0, it will be realised in the model A. Therefore, there'll be a tuple of elements A bar in the model A, satisfying this guard, the guard on the hth witness constraint, so AH. But since the model A makes all the witness constraints true, there'll be a witness, right? There'll be a tuple of elements B bar, such that A bar B bar satisfies this formula in the consequent of the witness requirement. Now take Tor to be the type of elements A bar B bar in some order. And it's therefore easy to see that Tor is going to be an H witness for W bar in the type sigma. So W bar will have a witness, contrary to supposition. If it has, since it has a witness, that witness must be in T, right? Because we are supposing that sigma was the first removal of a type of T, first removal from T of a type in T0, and so since it's the first removal, Tor is at that point still in T, and so it will have a witness, and so we can't remove it. We can't get going removing types in T0. So throughout the loop, all of the types in T0 will be contained in T. So T will include T0, and that proves the claim. So at the end of the until loop, we have T0 as a subset of T, and since the model makes the existential, the initial conditions true, there exists x chi x bar. Then there'll be a sigma in T0, which makes this true. And since T0 is included in T, we'll see that there'll be a type in T at the end of the loop, which makes the initial conditions true, so the algorithm will return yes as required. Proves the lemma. So we have a second lemma here. Let phi be a normal form formula of GFK, k-variable guarded fragment. Suppose that the algorithm sat-GFK returns yes. We claim that phi must be satisfiable. And what we'll do to prove this is we'll look at the variable t in this algorithm, in the algorithm sat-GFK, at the end of the algorithm. What do we know about this? Well, we have three facts. Number one, for every type Tor in T, Tor must make the universal constraints true. That's because every type Tor makes the universal constraints in T makes the universal constraints true at the start of the algorithm, and we'd simply get rid of types in the set T. We don't add any more. Fact number two, T contains no bad types because the algorithm doesn't terminate if there are any bad types. Fact number three, there exists some Tor 0 in T which makes the initial conditions true. because otherwise the algorithm wouldn't have said yes. So now what we're going to do is to construct a tree V. Each vertex mu of V will be labelled with some type in T, and I'll call that type sigma subscript mu, and it will also be labelled with a structure A subscript mu. And A subscript mu will be an isomorphic copy of sigma subscript mu. Remember, we can regard types as structures, and A mu will simply be an isomorphic copy of that structure. And F mu is the isomorphism in question. And the idea is that these structures A mu are going to be patched together to form a model of phi. Let's have a look at how we can view this schematically. So here's our tree V. Here's a vertex mu. It's associated with a type sigma mu and a structure A mu, and these two are isomorphic via an isomorphism which I'll call F mu. If sigma has a daughter in the tree, a daughter nu in the tree, then nu will also be associated with a type sigma nu and a structure A nu, and these will be isomorphic. And the idea is that if nu is a daughter of mu, then these types will in general overlap. In fact, more generally, if nu is a descendant of mu, the types may overlap. I'm sorry, the structures here may overlap. We're going to make them overlap in controlled ways, and that's why we will always take isomorphic copies of the types labelling the vertices. Okay, so that's the overall picture. Let's look at things in more detail. We'll define the tree V level by level, starting at the root, call the root mu0. We'll take the type labelling mu0 to be tor0. Remember, tor0 is a chosen type which satisfies the initial conditions. And we know there must be one, because otherwise the algorithm wouldn't have said yes. We also need to define the structure labelling the root, A mu0, and we'll just take that to be identical to tor0 and take F, the isomorphism, to be the identity function. So there'll be no problem there, and when we do that we'll see that A mu0 makes the initial conditions true. Okay, so now suppose that a vertex mu has been constructed. If, for some h, there is a tuple A bar in the structure associated with that vertex, such that A bar satisfies the conditions on the hth witness requirement, then what we're going to do is add some elements to the whole structure that we're creating, which will serve as witnesses. Okay, so we've got a vertex, suppose we've got a vertex mu, structure associated with that vertex, A mu, a tuple in that structure, and let's suppose that that tuple satisfies the guard on one of these witness requirements. Guard is AH. It's the hth witness requirement that we're interested in here. Well, since we have a tuple of elements satisfying AH, and since sigma mu and A mu are going to be isomorphic, we can find a tuple W bar of variables in this type, such that the isomorphism takes W to the tuple W to the tuple A. So in other words, the type sigma mu will satisfy will ensure that the tuple W bar of variables satisfies AH. Okay, so we've got a tuple of variables in the type labelling mu satisfying AH. But the set T of types contains no bad types, so there must be a witness. If there weren't a witness in T for this fact, then if there weren't an H witness for this tuple W, sigma would be a bad type. So we can choose a witness, tor. And we know that we've got an isomorphism rho from sigma mu to Tor, partial isomorphism, I should say, from sigma mu to Tor, such that the domain of this partial isomorphism includes everything in all the variables W bar. Now, if the image of that partial isomorphism isn't the whole of Tor, what we're going to do is we'll add a vertex nu to the tree, set that vertex to be a daughter of mu, and we'll make the type associated with nu to be Tor. So sigma nu is going to be Tor. And the intention is that we can define a patch, a structure, a nu, to provide the missing witnesses for the tuple a bar in the structure, in the patch associated with mu. So if you see, if mu is a vertex in the tree, the structure associated with it has a tuple satisfying an antecedent of one of the witness requirements. We'll add a daughter, nu, to the tree, make that a daughter of mu, and the patch, the structure a nu associated with nu is going to provide the witnesses required to make this witness requirement true. That's the idea. Now, noticing that and the way we choose this type is we know that there's a type which provides an H witness because there are no bad types. So let's choose this type from T. Okay, so letting rho be the partial isomorphism from mapping between sigma mu and sigma nu, that is to say Tor, we'll call the elements of the image of rho the old elements of sigma nu, that is the old elements of Tor, and all of the other elements nu. So if we look back to this picture here, we have we're going to have so I should go forward, so I've got a nicer diagram here, excuse me. So what we have here is vertices mu and nu. There is a tuple W bar which satisfies some predicate which is a guard of one of the witness requirements. We have a witness for this, and this witness is Tor, and we've added a daughter, nu, and associated with nu this type Tor. I'll call that sigma nu. And there's a partial isomorphism mapping between sigma mu and sigma nu. And that the domain of that partial isomorphism includes all of the elements in the tuple W bar. So they get mapped to some tuple of elements here. And these are the old elements, the elements in the image of rho I'll call the old elements, and any further elements in Tor I'll call the new elements. Okay, so what I've now got to do is define this structure A nu, because I've defined sigma nu, so that's witness type Tor, and I've got to define this structure A nu. So what do I do? Well, if we've got an old element of Tor, that corresponds to some element of sigma mu. So in other words, if we've got an old element of sigma nu, that corresponds to some element of sigma mu, and that will be mapped by the isomorphism f of mu to some element of this structure here. And what we will do is we will map this this old element of Tor to be precisely that element. We'll find out what variable in sigma mu it corresponds to, and then simply follow the mapping f of mu. In other words, we'll compose rho to the -1 with f of mu, and then we'll get an element, and that will be the element f of nu. If we've got a new element, then I'll just choose some brand new element not occurring elsewhere, and I'll define that to be f of nu. So I can now define a function f of nu to be mapping all of the variables in Tor to some new set of elements. The old elements of Tor will be mapped to elements already in a mu, and the new elements of Tor will be mapped to some new elements. And I can define a structure A nu on this set of elements by simply applying f to the structure sigma nu, in other words Tor. So that gives me a little structure A nu associated with the vertex nu, and an isomorphism between the type sigma nu and this little structure, and there'll be some sharing of elements corresponding to the partial isomorphism between the types here. Okay, so when I do that, you'll see that because of the way this thing was chosen, this structure A nu will contain witnesses, all the witnesses required for the elements in W, right? So all of the hth witness requirement will now be satisfied. So what you do is you continue the whole process. So starting with the root, make sure that all of for any witness requirements that you have, any guard on any of the witness requirements which is satisfied here, we construct a daughter and an associated patch, an associated model A nu, so that all of the witnesses required are satisfied, and you simply keep going on and you get a tree of patches. Because the patches are added consistently and form a tree, this naturally defines a limit structure. So you just take all the patches together, and that will give you a natural limit structure, and let's call that A. Notice that A hasn't been specified in respect of relations not belonging to different patches. So if you've got elements within a single patch, we've said everything about them. We've said what all the predicates all of the tuples involved satisfy. If you have a tuple of elements which don't belong to a single patch, say an element from here or an element from here that's not covered by a single patch, we haven't said what tuples they satisfy. Okay, but that's we don't have to worry about that, because what do we know? We know that however we complete this model, the following has been secured already. First of all, the initial conditions are satisfied because they were satisfied in this little patch down here. We know that all of the existential requirements are satisfied because if any tuple is known to satisfy an atom, then it must be in one of these patches, and witnesses will have been added when we added daughters for that patch. So all of the witness constraints will now be satisfied. Moreover, we know that all of the universal constraints within any patch have been satisfied, so we haven't violated any universal constraints. So to complete the model, we simply declare that any tuple not contained in any of the patches satisfies no predicates at all. So it can't have any additional witness requirements because it doesn't satisfy any predicates there. And it can't violate any of the universal constraints, because if you look at what the universal constraints are, is that they say, well, things like, some collection of objects satisfies this formula. This formula is an implication, and the antecedent of this implication is an atom, and by hypothesis, any tuple not contained in a patch satisfies no atoms at all, so trivially satisfies these universal constraints. Any tuple contained within the patch automatically satisfies the universal constraints because all of the patches did. And all of the types in T satisfy universal constraints, so they're automatically okay, they're patches. Okay, so when we complete the model in this way, we have a collection of, we have a structure A which satisfies the initial conditions, satisfies all the existential requirements, and satisfies the universal constraints, and therefore satisfies the formula phi. So we've proved the lemma. If the algorithm terminates with success, we can construct a model A of phi. Notice that the model we construct is infinite, and because we just keep going, this tree just keeps getting, it's a limit, it's an infinite limit, so the model is in general infinite. And I'll come back to that in just a second. So these last two lemmas ensure that the procedure sat GFK phi returns yes if and only if phi is satisfiable, so the satisfiability problem for the guarded fragment is decidable. Let's analyse the running time of the algorithm. So we need a bound on the size of t. We have to be a little bit careful because there's no limit on the arity of the predicates. Observe, however, that the number of atoms occurring in phi is at most the size of phi, the number of symbols in phi. And the only atoms that concern us here, the only ones we need to worry about, are substitution instances of the atoms that occur in the original formula phi. We don't care about anything else. They might as well make all other atoms false. So if phi features at most k variables, there are at most k to the k substitutions to consider, and hence at most the number of symbols in phi times k to the k atoms that we need to worry about. So the number of types is essentially bounded by 2 to the power of the size of phi times k to the k. That's the total number of atoms we ever need to consider. I'm sorry, the total number of types that we need to consider. So that's a bound on t, and let's have a look. We then have the following theorem. The problem, the satisfiability problem for the guarded fragment is in 2ExpTime. For every k, the satisfiability problem for the k variable guarded fragment is in ExpTime. So why is that true? Well, let phi in GFK be given. We can convert phi in polynomial time to an equisatisfiable formula phi prime in GFK plus 1 in guarded normal form. It may be that the number of variables increases by 1, but you can certainly convert in polynomial time to something in the guarded normal form. So we'll call this algorithm sat GFK on phi prime. Now, t may be assumed to satisfy this inequality for phi, so I suppose phi is here really phi prime, so k gets increased by 1. And this bounds the number of executions of the until loop, right? So we don't execute the until loop more times than there are types in t, because each time we go through the until loop in the algorithm, we check out at least one bad type. And moreover, determining whether one type is an H-witness for another can be carried out in time polynomial in the sizes of the types and the size of phi. So clearly exponential in the size of phi. So this algorithm, when we call the algorithm sat GFK on phi prime, the normal form version of phi, the original formula we had, that runs in time doubly exponential in the size of phi. So it's this bound here, and it's singly exponential if k is treated as a constant. So if k is a constant, in other words, we're looking at GFK, it is singly exponential, and that proves the theorem. So we have an algorithm which is correct, which runs in doubly exponential time, singly exponential if we regard the number of variables k as a constant. Okay, so that's the main technical content of the paper. So a little bit of history just to finish off. So the guarded fragment was first defined by Andrejka, Nemeti and Van Bentham in 1997. And they showed the decidability of satisfiability. The detailed complexity bounds were first given by Erich Gradel. They follow essentially immediately from the Andrejka, Nemeti and Van Bentham proof. So that the upper bounds are more or less straightforward. The lower bounds are not quite so obvious, but they can Gradle nevertheless gave proofs of them, so there are tight lower bounds for these. Now, remember I said that the model constructed in the proof of one of the lemmas explaining the correctness of our procedure is infinite. So this secures the decidability of satisfiability, but not the decidability of finite satisfiability. And in fact, it's not at all obvious that the guarded fragment has the finite model property. This does not follow from the proof of the correctness of our algorithm. However, by employing a celebrated theorem on the combinatorics of finite graphs due to Hrushevsky, Gradle was able to come up with a proof that the guarded fragment does in fact have the finite model property. So we have the following theorem. The guarded fragment has the finite model property, and so in other words, its satisfiability problems and finite satisfiability problems are the same. The satisfiability problem for the guarded fragment is 2 ExpTime complete, and for every k greater than 2, the satisfiability problem for the k variable guarded fragment is ExpTime complete. So matching lower bounds were provided. An elementary proof of the finite model property for the guarded fragment is possible. However, it's still rather difficult. You don't need this very complicated combinatorial result, but it is nevertheless still rather difficult and will not be given in this lecture.